Hi everyone, my name is Nicola, and in this video we're going to figure out what the pressure is at the bottom of a vessel containing water with a height of water h. We're also assuming that the water is exposed to atmospheric pressure. So this is the dimensional analysis playground which we will be using to solve this problem. This also has a direct link to the documentation for dimensional. So if we click on that, this pulls up the documentation page and some videos for this software package. So I'm going to head back over to the dimensional playground. So in order to find the pressure at the bottom of the vessel, we're going to have to relate pressure to height somehow. And there is a formula that relates this. This is the simple formula that relates pressure to height, where P as pressure equals the density of the fluid times the gravity times the height. The first thing that we're going to need to do is define these variables here. So the density of water we know is 1 gram per cubic centimeter, so I'm going to input that into a variable here. So I've just defined the density of water as 1 gram per cubic centimeter, and I can display that in this window here by using that latex function. And so here it is. Our density of water is 1 gram per cubic centimeter. If I wish, I could convert that into a different unit system, but dimensional will automatically convert everything it needs to in the background. So we don't have to do that, but I'll just demonstrate just to show how it's done. So here I show the density of water the way that we defined it, grams per cubic centimeter, and I've also said the density of water as kilograms per cubic meters. And so we see both of them displayed down here. So it is either 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. Like I said, we don't need this one, so I'm going to get rid of it for now. And then we're going to move on to the next variable here, which is g. So g is the acceleration due to gravity on Earth, which is 9.81 meters per second squared. But if we go to the documentation here and we check the units here, or actually we check these units, these are the built-in units in the package, we see that G's is already represented in here. So instead of redefining meters per second squared, we can just set it to 1g. So I'm going to define this acceleration as 1g. And so I've defined it here as 1g, and I'm going to display it the same way. If we want to verify that it is about 9.8 meters per second squared, I can do that same thing with the .as function. And here we have it. 1g is about 9.807 meters per second squared. Now look what happens when I change the unit conversion to where the dimensions are compatible. So if I try to set gravity to meters per second cubed, we're going to get an error over here where the dimensions on g's don't match the dimensions on meters per second cubed. So then you know that there's a problem here. We can actually combine these two terms. A density times a gravity is known as a specific weight. Just to simplify the formula a little bit, I'm going to call a specific weight capital W. So now we have the pressure equals the specific weight times the height of the fluid. And so this result here is the specific weight of water here. And this relates our pressure to our height. And so we're almost done here. So the next step is we're going to need to define the height of that container, or the height of the fluid within that container actually, and multiply that to the specific weight, and then we will finally determine what the pressure is at the bottom of that container. And so what I've done here is I've said the height of water is about 100 inches, and all I need to do now is multiply that by the specific weight. And that's it. And so we now have our pressure defined in this variable. And so let's display it. So now we know that our final pressure is 100 inch gram G per cubic centimeter. Pretty obvious, right? I think to most people, this doesn't look like a pressure at all. This is one where we should convert it to something else, like PSI. We could convert this to something else, like bars. And now this makes a lot more sense. With 100 inches of water, the bottom of the tank is about 3.6 psi or 0.2 bar. This is a gauge pressure, so if we want the absolute pressure, we could add a single atmosphere of pressure onto this. And so what I've done here is I've added a single atmosphere of pressure onto our result pressure here. So just real quick, if we wanted to do the other way around, if we knew the pressure at the bottom of the container and wanted to determine the height of the fluid, we could just solve for H. So then here we know that the height of the fluid is the pressure at the bottom divided by that specific weight. So I'm going to just rearrange the code a little bit here. Alright, so what I've done here is I have defined the pressure at point 1 to 5 psi, and now we're going to determine what the height of the water is. And again, we have the height of water, which is 5 psi cubic centimeters over grams Gs. And again, that doesn't really quite make sense, so we're going to convert this to something like meters. At 5 psi, we have about 3.5 meters of water in that container. And that's about it. I hope you enjoyed the video, and see you next time.